Day 138 Notes, Pre-Calculus. Today we discuss the ambiguous case number 2, also sometimes called the swinging side. Case number 2 from our 4 cases that we listed on Monday is the side-side angle case, where we have two side lengths that are known and an excluded angle, an angle on the outside of those two sides. The problem that we sometimes run to is that when we're given two fixed length sides and an excluded angle, the swinging side might be too short to actually complete a triangle. It might be just long enough to make a right triangle. It could be long enough to form two different triangles, or it could be too long to form anything but one right triangle. Well, let me try to explain. I'll show you an animated example here. Suppose I'm given two fixed sides. One side has a length of 10, one side has a length of 4, and an excluded angle. This angle is going to be set to 30 degrees. So if I have a side, and an angle, 10, 4, and 30 degrees, no matter where I position this side here, this side length of 4 is always going to be too short to complete a triangle. And I know it's not going to complete the triangle here because it will never reach this imaginary dotted line that would contain a 30-degree angle in this exterior. Now, if we didn't have to hold that 30-degree angle, then we could clearly create the triangle as a connection between point B and this point A. But since I have to maintain this 30-degree angle, that's just not a possibility. Now, if I extend the length of B to be 5 units long, you'll see that this side length is exactly half of this side length now. Something interesting occurs because I can swing this leg down to the point where it actually creates a right triangle. I know my measurement's hidden here, but this still reads 30 degrees. You can see it over here. This alpha measurement is 30 degrees. The sine of 30 degrees is 1/2. So the relationship between the opposite side and its hypotenuse must be half. So 5 is half of 10. That's what verifies to me that this is a right triangle. Now if I start sliding my angle back to the left, or if I form this pendulum here, you'll see that it only creates a triangle in this one spot. Now let's suppose I make this side length just a little bit longer. Let's say that I was presented with two sides, a side length 10 and a side length 6, and this 30-degree angle. Well, if you look here, I could form a triangle at this point, yet this triangle would be completely different than the triangle formed at this point. Yet both contain a side length of 10, a side length of 6, and an angle measure of 30. Just so happens that the third side in this position has a side length of 5, or 5.35 approximately, whereas the triangle in this position is about 11.82. And that doesn't only happen for angle measures of 30 degrees. Let's open this up just a little bit. Let's create an angle of 65 degrees, and I don't know, maybe we can reduce the size of this initial side length here. So suppose we had a triangle that was 7 units long on one side, 6 units long on another, and it has an angle measurement of 65 degrees. Does that produce a triangle? Well, let's see. If I swing this leg down, you'll notice that it's a bit too short for this to reach a 65-degree angle. So having a side length of 7, 6 is too short, provided we have an angle measure of 65 degrees. But if that second side length was maybe 7 units long, sure, we can produce a triangle here. That's unique. And, well, this one over here is not going to be unique because the two side lengths are exactly the same, 7 and 7. This forms a perfectly straight line at this position. Now, it looks like I'm creating a triangle as I drag this to the right here, but keep in mind this side length on the right-hand side should be 7 units long, and it wouldn't be 7 units long if its point is formed here. So I'll have to back it up and show that this creates only one triangle in such position. I'll make this file available to you should you choose to download it, and you can investigate a little bit further such ambiguous cases as we move forward through the unit. You'll have to download and install the program called GeoGebra that I use to create this file, but you'll be able to manipulate this and further investigate this idea of the swinging leg and the ambiguous case, case number 2. Now what that means for us in class is that anytime that we encounter case number 2, we need to double check our calculations and make sure that we solve for all possible triangles. This is problem number 19 from the text, and we clearly have case number 2 because we have two sides and an excluded angle. And this is where sketching an accurate picture really comes in handy. So I'm going to try my best here to sketch this freehand. I've got one side length, and I'm going to call this angle here A. This will be the 110-degree angle. Opposite of that angle is going to be side length A. I have to use a lowercase letter a here. And that A value is equal to 28 units. Side length B would be opposite of corner B. So this angle B has a side length opposite of it equal to 15 units. And you'll notice that it's much shorter than this side length A, not quite half. And let me indicate this angle measure here to be 110 degrees. What we need to verify with our law of sines is whether or not I've sketched this triangle correctly, and whether or not we could produce more than one triangle that fits these three descriptions. Now I might only use a portion of the law of sines. I know that sine of A divided by A would be equal to sine of B divided by B, but I don't need to work with sine of C because I don't have that information here just yet. So let's fill in the data that we know. Sine of 110 degrees divided by 28 should be equal to sine of B degrees divided by 15. When I solve for sine of B, I can still cross multiply, then divide, and that should tell me what sine of B is equal to. That'll give me some indication whether or not we'll have one, two, or no triangles based on this piece of information. So I know that sine of B would be equal to 15 times sine of 110. That's my cross multiplication. And I would divide by 28. So sine of B, based on this setup here, you can go to the calculator and find that result. I have a fraction here. 15 times sine of 110 divided by 28 is equal to negative 0.0237. Well, that answer doesn't look right, and wouldn't you know it, my calculator is set in radians right now. So let me fix that. It needs to be in degrees, since our given information was in degrees. And I'll recalculate. There we go. 0.5034. So sine of B is 0.5034. What I'm looking for are angle measures B so that sine of B is equal to 0.5. Now if this was exactly 0.5, it'd be easy to solve. But since it's a decimal value, we don't know exactly what the answer is going to be. But I do know that it will occur in two positions between 0 and 180 degrees. Now that's important for us because these two angles could produce angles that would satisfy the argument in this triangle. So sine of B would be the y value of this point as it crosses the x-axis. My job is to use a calculator to find out what these two angles are. Let's find the first one. Sine of B can be, or we can use the inverse sign to isolate B. So let's apply the arc sine of 0.5034. So we'll use the arc sine of 0.5034, and that comes out to be about 30.2252 degrees. 30.5, oops, that's 30.2252 degrees. Now that's one option for angle B. It might be 30 degrees. Now the other option would be 180 degrees minus that. So 180 minus 30.2252, and 180 minus 30.2252 is equal to 149.7748. 149.7748. Now, this one's not going to work for us, and I know that because one of my angles is already 110 degrees, and if my other angle was 149 degrees, that would be greater than 180 degrees, and we can't have that inside of a circle. So the only acceptable answer is to find that angle B is equal to 30.2252 degrees. So let's start finalizing our answers now. We can solve this triangle, and we have confidence now knowing that there's only one triangle that's going to meet these requirements. Angle A was 110 degrees. Angle B must be 30.2252, and angle C would be the difference between these two and 180 degrees. So 180 minus 30.2252 minus the 110 that we know that A is, this tells me that angle C must be 39.7748. 39.7748. Now we were also told that A is equal to 28 units, B is equal to 15 units. Now all that's left is finding length C. So I'll go back and complete the law of sines now. Sine of C would be divided by C. And to complete this, sine of angle measure 39.7748 degrees divided by C can be used, and we can cross multiply and divide for that solution. I'm going to use the data that we had over here for sine 110 and 28. That way I don't have to use rounded data in sine B. So when solving for side length C, that would be equal to 28. Let me show this here. C is equal to 28 times sine of 39.7748. All of that divided by sine of 110 degrees. So let's perform that calculation. 28 times sine of 39.7748 divided by sine of 110 degrees. And that tells me that third side length, side C, is 19.0633. 19.0633. And we now have solved that triangle, and we know that it's a unique solution. Let's take a look at number 22. We again are dealing with case number 2 because we have two sides and an excluded angle. So I might start with a sketch here if I can draw one. Angle C is 38 degrees. Let's try to make this a little bit more shallow. 38 degrees might look something like this. So this is angle C. Side length C is 42 units in length. So this will be 42 units. Now I'll call this angle up here B, and I'll call this angle down here A. So if this angle is B at the top, then side length B is at the bottom. And we've got to decide if this triangle will exist as a unique triangle or if more than one solution can exist for this known piece of information. Let's start with the law of sines. Sine of C divided by C must be equal to sine of B divided by B. So sine of 38 degrees divided by 42 must be equal to sine of B divided by 45. Therefore, sine of B must be equal to 45 times sine of 38 divided by 42 because of the cross multiplication and division. So finally, sine of B would be equal to 0.6596. And I got that solution by going to the calculator and obtaining the result, 0.6596. So I'm going to start thinking to myself here, if I looked at a unit circle, what angle B would give me a y value of 0.6596. And again, there could be two of them. These 2 points here could have a y value pretty close to this. So one of the results is going to be sine inverse of 0.6596. And the other might be the supplement of that. In this first case, B might be equal to 41.9624. And I got that from calculating sine inverse of the decimal we just found a moment ago, 41.2694. And the other could be the supplement of that. So 180 minus 41.9624 is equals 138.7306. And if I'm not mistaken, that 138.7306 plus the 38 that we know to exist to be true initially is still under 180 degrees. So it is possible for B to occur in either value. So what I might do is label these slightly differently. I'm going to call this first option B1, and I'll call this next one B2, because there are two different triangles that are formed with these given data values. So let's find out what the rest of the triangle might look like. I'm going to set up two results here, A, B, C, and A, B, C. I'm going to call these B1 and B2. I'll have those separated. And for each of those, we're going to have different side lengths, A, B, and C, and A, B, and C. Well, in both cases, C has to be equal to 38 degrees. That was given to us. In one case, B might be 41.9624, and in the other case, we'll have a B value of 138.7306. Now, in this first case, 180 minus 38 minus 41.9624 would tell me what A is equal to, and that result comes out to be 58.0376, 58.0376, whereas in this other case, 180 minus 138.7306 minus 38 degrees would equal our other A value. And I just recognized a mistake that I made in that first calculation. It should have been 180 minus 38, and so on. So that angle measure is actually 100.0376, whereas in this second case, the other angle measure is 3.2694 degrees. So now we have three known angle measures for each triangle. Let's find those missing sides. Now in both cases, B is equal to 45 units in length, and C is equal to 42 units in length. So all we need to do is find side length A. Now I know that sine of 100.0376 divided by A in this first case must be equal to sine of 38 divided by 42. I'm using C here because those are nice round numbers, whole numbers that we don't have decimals for. And in this second case, sine of A, which is 3.2694 units, over A must be equal to sine of 38 over 42 as well. So we'll use our cross multiply and divide shortcut to find out what A is. So we'll cross multiply and divide in both cases to find A. And having entered those calculations into the calculator, I see that the side length A in the first case would be 67.1751 units in length, and for the second case we'd have a side length of 3.8906 units. And there you have it, side length A in two different cases. These are two unique triangle solutions that met the original criteria. Angle measure C equal to 38 degrees, side length C equal to 42, and side length B equal to 45. Those three data points were required, yet they still produced two different angles, two different triangles. Number 28 is going to be omitted from today's notes due to the length of the video so far, but I think you should be able to try this on your own and check your solution against my sample solution tomorrow in class. Please let me know if you have any questions as we move forward.